A warm welcome to all the viewers for the course Strength of Materials AME 302. Myself Thea Pal, Assistant Professor of Department of Mechanical Engineering, JIS College of Engineering, is going to give a detailed lecture on pressure vessels. So this is basically included in module number 6 for the course Strength of Materials, and here today we are going to discuss the pressure that has been exerted inside the pressure vessel. So in engineering field, if we daily come across the various vessels of cylindrical or spherical, then I must say that you have gone through some tank, compressor, as well as some boiler, compressed air receiver, etc. This type of element, they are basically some day-to-day example of our engineering fields, and basically this container are filled up with either some steam or some gases. So when they are filled with what I will say, this vessels, when they are filled with due to steam or compressed air, basically they insert or exert internal pressure inside it. Okay, and this pressure basically helps them to generate some sort of tensile stresses over the thin cylinder of the particular vessel. But when they are empty, they get focuses with the atmospheric pressure internally as well as externally. But in that particular cases, what happens? The resultant gets 0. But when it is filled with some steam or compressed air, they basically exert a pressure on the thin wall of these pressure vessels, and this stress that basically generate on the thin wall are always the tensile stress. Okay, so today we are going to see that if this pressure is getting exceed the permissible limit, then it can get break also. So this break can occur basically in two ways. First of all, it can split into two troughs, that is through longitudinal way, and if I talk about it, can split into two cylinder, that is from the mid of the section of that particular cylinder. So this can happen in this particular cases. So before we go with the detailed lecture of the pressure vessels, let's have a look what are the contents of today's lecture. So initially we will be starting with the stresses in thin cylindrical shell. Then we will be discussing some analysis of thin cylindrical shell with closed flat ends, and then we will be discussing the hoop stress or circumferential stress. And in the part 2 lecture of this pressure vessels, we will be basically discussing the strain in the cylindrical shell as well as strains in the sphere. So these are the content that we are going to cover up in this particular module under pressure vessels. So this pressure vessels module will be illustrated in two different lectures. So first lecture we are going to cover up the stresses in thin cylindrical shell, as well as we are going to cover up the analysis of thin cylindrical shell with closed flat ends, and we are going to discuss the hoop stress, or which is known as the circumferential stress. We are going to have a look in this particular content, and finally in the second lecture we are going to discuss about the strains in cylindrical shell, strain in sphere, and so on so. So without any further delay, let's have a look at the next slide. So what you can see is that stresses in thin cylindrical shell, as I have already told you that if I compare some day-to-day engineering field product, like if I come across the vessel of a cylindrical, it can be spherical also in shape, which may containing some fluids such as tank, boiler, even compressed air receiver, etc. So the generally this particular wall of such vessels, what I would like to say, they are very thin as compared to their diameter. So whatever may be the diameter, the wall is much more thin with respect to that particular diameter of that particular container. So what happens, the vessels when they are empty, they are subjected to some internal pressure as well as external atmospheric pressure. So in that particular case, what happens, the resultant is always 0. But when it is filled with some compressed air or when it is filled with some gaseous or some fluid, it basically feels some sort of internal pressure, and there the pressure helps to develop a tensile stress in the wall of the cylinder. Why? Because the thickness of the cylinder is much more less than the compared to the diameter of that particular cell. So if I have a look here today, that basically the stress that basically generate in the thin cylindrical cell are of 3 types. One is longitudinal stress, second is hoop stress, which is very commonly known as the circumferential stress, and third is the radial stress. So now what we are talking about, the longitudinal stress. So if you see this longitudinal stress, what happens, that is due to some internal fluid pressure. These are tensile, but due to external fluidic pressure, these are compressive too. So if your thin cylinder is completely filled up with some fluid, then obviously this fluid will exert some sort of pressure. And the most important thing is that if the fluid is exerting the pressure due to the internal fluid that is present inside the cylinder, then there they are going to get some sort of tensileness. So the pressure basically that generate the stress in the thin wall due to internal fluid is due to this tensile, what I will say, tensile load you are giving, that's why a tensile stress is occurring. But if I talk about some external fluid pressure, these are basically compressive in nature, and that's why what happened, there is also stress is occurring. So ultimately the thing is that cylinder wall is thin as compared to the diameter of the cylinder. So whatever fluid may be there, internal, or if you think about the external also, due to external some problem, they are providing some sort of load, then that is compressive load it can be, and if it is internal, then it is exerting some tensile pressure also, and this pressure is particularly what helping to generate the stress on the thin cylinder. So in thin cylindrical cell, these are uniform across the thickness of the cell. So whatever may be the thickness, the pressure or the stress that is evolving here, basically the stress that is evolving is basically uniform throughout the section. So you have to remember that longitudinal stress is none other than stress that occurs due to internal fluid pressure. Now these are tensile if it is due to internal fluid pressure, but if it is due to external fluid pressure, then these are compressive too. So in thin cylindrical cell, these are uniform across the thickness of the cell also. Now if I talk about the hoop stress, it is also known as circumferential stress. So due to internal fluid, now what I will say, that is about the hoop stress. Okay. Now these occur basically due to the internal fluid pressure. These are basically tensile in nature, and in thin cylindrical cell, these are also assumed to be uniform. So for hoop stress also, if you have a look here, that is due to internal fluid pressure, these are tensile in nature, and in this particular thin cylindrical cell, these are assumed to be uniform all throughout the section. Now we are talking about the radial stress. So in case of radial stress, what happens, this is basically occurs Because the magnitude is very small. Radial stress, it's basically the magnitude is very small. Hence, it is neglected for all the practical purpose. However, its value at internal phase equal to the fluid pressure at the outer phase is equal to the atmospheric pressure. So, if you talk about the value for internal phase, then you must say that the value is just equal to the fluid pressure. But if you talk about the outer phase, then its pressure value is always equal to atmospheric pressure too, and that is also 0. Now what happened is there, I must say that however you see, I must say that radial stress, basically the magnitude is very small. That's why we are just neglecting it. And the most important thing is that, as I have told, that internal phase value is always equal to fluid pressure and outer phase value is always equal to atmospheric pressure, and that is equal to your 0. But for all the purpose, its value is taken as 0 from inner to outer surface too, because the value is so small, or even you can say the magnitude is so small that it is neglected for all purposes. So here from this particular slide, we are very familiar with longitudinal stress, hoop stress as well as radial stress. Now let's have a look at the next slide. Now just have a look at the longitudinal thing. So you can see this is the analysis of a thin cylindrical cell with a closed flat end. So the end, you can see it is a closed flat end, and this is longitudinal stress. This is longitudinal stress which is represented by sigma L, and you can see the length is L and the diameter is D. So as compared to the diameter of this particular cell, you can see the thickness, that is the T, here it has been represented by T, it is also very small, and the fluid is there inside the cylinder. That's why it is ejecting some pressure. It is ejecting the pressure where? It is ejecting the pressure in the wall, in the inner wall. And this here, what happened, you can see this is sigma L has been denoted this particular point, at this particular point. These are basically what? The longitudinal stress that are occurring here. So as compared to the longitudinal stress, you can see the pressure, internal pressure has been assumed in this the wall, and the stress, longitudinal stress is also occurring in this particular thickness of the wall. Now if I talk about the hoop stress, then in this particular condition you are able to see this is a circular cylinder, and you can see the thickness of the cylinder also, and you can see this hoop stress, which is also known as circumferential stress. It is exerted in the wall of the particular cylinder. This arrowhead is representing the pressure that has been exerted in the thickness of the inner wall of that particular cylinder, and you can see this particular point, this particular point and this particular point, whatever may be this particular point, these all are hoop stresses, and it is represented by sigma H. So from this pictorial view, hope it is clear how basically the longitudinal stress look or the hoop stresses look. Now if this pressure is exceeding the permissible limit of that particular container, then the product will be getting break, or it is getting failure through the mid of the section. So it will be split into two trough. But if you are going for the hoop stress, if the pressure exceed the circumferential stress and all the circumferential state, or I mean to say the permissible stress, then what will happen? The cylinder will get split into two sections. So this can occur into two sections, the cylinder, and one it can go through for longitudinal, it will go through the split through what? The trough. Now just have a look in this hoop stress or circumferential stress. So basically you can see this is a thin cylindrical cell, and we have considered the diameter as capital D, and you have to consider the thickness of the cell as small t, and we have considered the length as L. So this is the thickness you can see of T, and this is basically the diameter of the cell, which has been considered as capital D. So you have considered this one as capital D. If I consider this is the diameter, then it will be considered as capital D. Okay. So now what is happening is that it is subjected to an internal pressure that is to be considered as capital P, and due to this internal fluid pressure, there is also a bursting force which has been already developed, and its tendency is to split the cell into two parts. So as you can see that this is basically splitted into two parts. That means inside there was some internal fluid pressure, which is very commonly known as the bursting force, and this bursting force is developed and it had got a tendency to split the cell into two parts. So if I ask you, what is the equation for bursting force due to pressure? Now bursting force is basically denoted by FB, and it has been told that to calculate the bursting force we need to know the value for pressure and its projected area. So bursting force is none other than the product of pressure and projected area. So what I have considered as a pressure, that has been termed as P, and we are multiplying with that the projected area. So what is the projected area? If D is the diameter and L is the length, then the projected area is D into L, and pressure you have considered as P. Next, we are talking about hoop stress. So whenever we are talking about the stress, you can see that hoop stress basically include in material that resists the splitting of the cell due to the bursting force. So hoop stress is included in the material, and you have to consider that material has to resist the splitting of the cell due to this bursting force. So whenever we are talking about the resistance force, it is basically represented by F suffix R, that is equal to hoop stress into resisting area, because all of you know that stress is none other than force per unit area. All of you know that stress is the ratio between the load per unit area. So if I want to calculate the resisting force that is represented by Fr, it is none other than hoop stress into your resisting area. So hoop stress is been denoted by sigma h, I have shown you in the figure, and resisting area is what? Which portion is resisting? That portion area we need to find out. So you can see thickness is this side also there, and you can see this side is also there. This two wall you are facing the thickness. So that's why you have written 2 into T into L. So this is your projected area for the thin cylinder. So resisting force is equal to sigma h into 2 into T into L. Now for equilibrium, you know that resisting force is equal to the bursting force. Again I am telling resisting force is equal to bursting force, because we have considered the portion is in equilibrium condition. So if I talk about the resistance force, you know the value is sigma H into 2 into T into L, and bursting force is known as capital P into D into L. Now if you equate the equation, then what you will get? You will get sigma H is none other than PD by 2T. What is the value for sigma H? That is the hoop stress. PD by 2T. P is what? The pressure. D is the diameter of the thin cylinder by twice the thickness of the cell. And this is basically tensile in nature. Now you are here to have a look at the longitudinal stresses. So in case of longitudinal stress, you just see that we have considered a thin cylindrical cell, and that is also subjected to internal pressure, and due to this internal fluid pressure, longitudinal stress will induced in the material of cylindrical cell. And since there is no bending, therefore longitudinal strain will be uniform in all longitudinal fibers too. So let's have a look for the longitudinal strain or longitudinal stress, which will constantly which will be constant across the thickness of the entire cylinder. So again I would like to say the process is same. The body has to be in equilibrium, and if the body is in equilibrium, that means bursting force is always equal to resisting force. So what you have to do is that this is basically a thin cylinder and fluid is there inside, and this fluid is exerting some internal pressure. These are the internal pressure, and this has been exerted over the wall, and you have considered the length as small l, and here you have considered the thickness as T. So in case of longitudinal stress, what I have done is there you are taking a cross section of this particular through XX. So longitudinal stress will be developed where? In this particular portion, which is denoted by sigma L. This is denoted by sigma L. This is your longitudinal stress. So what is the bursting force equation? Again same, pressure into your area, projected area. So what is the projected area? That is D has been given to you. So pi by 4 into D square. So this is the value for your capital D, and you have got the bursting force as FB, which is equal to P into pi by 4 into D square. Now resisting force. If I talk about the resisting force, then you can see this is represented by Fr, and this is also same thing. What is the stress you are including? That is longitudinal stress. That's why you have mentioned here sigma L. And what is the projected area? That is, you can see this is the thickness and diameter has been given to you. The area is equal to pi into D into T. So your resisting force is equal to sigma L into pi dt. So if I equate the equation, because they are in equilibrium condition, so your resisting force is equal to your bursting force. So here you can come to a conclusion, that is bursting force is equal to P into pi by 4 d square, and your resisting force is sigma L into pi into d into t. So if I ask you what is the value for sigma L, that is the longitudinal stress, then obviously your answer will be sigma L is equal to P into D by 4T. Again I am repeating, the longitudinal stress value will be determined by P into D by 4T. So you have a look here. I have already told for longitudinal stress also the value is P D by 4T, as well as if you have a look at this particular thing, that is for hoop stress, then here also you can see that is for hoop stress the value for sigma h is none other than P into D by 2T. So if you have a look in this particular content that I have already discussed today, it's all about the hoop stress, circumferential stress, I mean to say hoop stress is also known as circumferential stress, and if I talk about the longitudinal stress, then you can see the value calculation process is same, but the value is something different. So just have a look at this particular thing once more so that it is perfectly clear to all of you. For hoop stress, you have to consider a thin cylindrical cell of diameter capital D, and the thickness has to be considered as small t, and you have to consider the length as L. And there you are seeing that if hoop stress is induced in material to resist the splitting of the cell due to the bursting force. So while we are calculating the entire hoop stress or circumferential stress, we are basically dealing with two types of stresses, or I mean to say two types of forces also. One is the resisting force, another is your bursting force. So whenever you are talking about the resisting force, then it is none other than the product of hoop stress into resistance area. But if you talk about the bursting force due to pressure, it is none other than pressure into projected area. So pressure is equal to P into pi, I mean to say P into D into L, and for resisting force it is sigma h into 2 into T into L. And if you come to an equilibrium condition, then I must say that resisting force is equal to your bursting force. And what you can see is that for hoop stress or circumferential stress, you can see that the value for sigma h is equal to PD by 2T. And if I have a look for the longitudinal stress, what you can see is that this is a particular cylindrical cell which is subjected to some internal fluid pressure, and you can see the diameter has been considered as capital D, the length of the cylinder has been considered as capital L, and the thickness has been considered as small t. And here what is important is that you are making a section that is through XX section, and you can see how the pressure is exerted in the thin wall. And you can see the stress has been already developed here, that has been denoted by sigma L in both the end of that particular cylinder, you can see. So what you have to do is that again the same thing, that is there is a bursting forces occurring as well as resistance forces occurring, and if you want to be in equilibrium condition, then what must I have to do is that you have to equate the equation, because in equilibrium condition both the bursting force as well as the resisting force both are equal. So resisting force is none other than pi by 4, I mean to say resisting force is known as pi into D into T into sigma L, and that is equal to your bursting force, that is P into pi by 4 into D square. So if you make a equation, if you solve the equation, then you will get the value for longitudinal stress is equal to PD by 40. But if you think about the longitudinal, I mean to say circumferential stress, then the value will be sigma h is equal to PD by 2T. So for numerical purpose you need to know about the entire thing. So finally we came to the end of this particular lecture, where I have already told that these pressure vessels will be subjected into two sections. I mean to say the lecture will be in two parts. In the first part we are just going to discuss about the stresses that have been involved in the thin cylindrical pressure vessels, and I have already mentioned you about the longitudinal stress, I have mentioned you about the circumferential stress, which is also known as hoop stress, and finally we have also discussed about the radial stress. And since you know the radial stress value is so minimum, the magnitude value is so minimum that we are considering it as 0, or even you can say we are considering at, or we are neglecting it. So all of you, if you have liked the video, then please stay connected with me, because in the next upcoming lecture I am going to give more details regarding the strain that has been evolved in the thin cylinder, that is for the pressure vessels. We are going to discuss elaborately. So hope you have understand from this lecture that what are the stresses that are been involved in pressure vessel, that is also for thin cylindrical cell, and you can see that how the longitudinal stresses basically occurs, as well as how the hoop stress or circumferential stress occurs. So if you have liked the video, then please stay connected with me and follow my channel and like the video, subscribe the channel too. Thank you viewers for watching the video. Please stay connected with me. Thank you.